Air Force scientists produced major space food innovations. These included new coated, bite-sized food cubes that did not flake in zero gravity, and new space food feeding systems. Most important, however, was Brooks scientists' contributions to the creation of new space nutritional requirements that benefited astronauts as well as people on Earth. Consumers have appreciated the convenience of commercial products adapted from Air Force-developed space food innovations, such as prepackaged menu items in measured nutritional portions. The then unknown long-term physiological effects of weightlessness also led to extraordinary Air Force scientific inquiry. Brooks Air Force Base became the venue for one of the most unique series of simulated weightlessness experiments in the history of America's space program.
Well, remember, you couldn't study weightlessness on Earth because we're subjected to gravity. But what we did do is made an analogy to bed rest.
Called Project Bedrest, dozens of airmen volunteers made simulated long-duration space voyages to Mars while confined for weeks in beds. During the 1960s, these studies primarily investigated physiological deconditioning caused by prolonged immobilization. Dr. Hans George Klaumann, chief of the Air Force School of Aerospace Medicine's Department of Space Medicine, inaugurated bedrest studies at Brooks.
He was interested in protecting the astronauts in spaceflight because he already knew somehow what they were going to encounter under weightless conditions. And that's the reason he started this bed rest study. Well, it was to find out what happened to the astronauts in prolonged spaceflight with lack of exercise and lack of movement. That was the whole purpose of it.
While similar studies have been subsequently conducted by academia and NASA, the Air Force pioneered bedrest-based weightlessness simulation.
Gravity has a perpendicular force like this, perpendicular to the surface of the Earth. And so human beings are like water towers, except we have blood and fluid in our body. And so gravity pulls you down. If it wasn't for gravity, you wouldn't weigh anything. But when you lie down perpendicular to the force of gravity, it doesn't have any effect on you. And so bed rest is very much like weightlessness. So we did a lot of studies on bed rest to see what happened to cardiac performance and other matters related to bed rest, and made it as an analogy to spaceflight.
Air Force scientists at Lackland Air Force Base's Wilford Hall Medical Center had discovered in 1962 that prolonged bed rest immobilization contributed to bone density loss. They also knew that mechanical stresses, such as those produced by weight-bearing and muscle tension exercise, are needed to maintain normal skeletal mass. In the absence of such stimuli, bone degrades and is susceptible to fractures. Project Bedrest became an important test venue for validating the scientific theory that prolonged weightlessness exposure leads to human physiological deconditioning. NASA was concerned that cardiovascular deconditioning, muscle atrophy, and calcium loss leading to early onset of osteoporosis in astronauts could pose serious problems for future spaceflight missions.
Well, they would take these young, healthy airmen, strong, healthy guys, and put them in bed rest studies and not let them move. They would keep them in bed and they'd bring their food to them, and they just had to stay motionless, no exercise, whatever. But those young airmen were healthy and strong, and after 30 days of bed rest, they were basket cases. They were just weak as kittens, and it affected a lot of them differently as far as their physiological parameters.
Air Force innovation at Brooks led to the invention of a device used to counter long-term weightlessness deconditioning effects on human physiology. The Total Body Exerciser was developed by Air Force physician scientists Drs. John Ord and William Thornton. The device was used in a 4-month Project Bedrest study conducted in 1969 at Brooks. The Total Body Exerciser was designed for use in spacecraft to simulate lifting weights in a 1G environment. It was tested by 8 volunteer airmen during 2 16-week protocols. The control phase allowed volunteers 20 minutes of exercise daily using the Total Body Exerciser. To maintain simulated weightlessness, volunteers were transported to the device and lifted into position. Volunteers were not allowed any physical activity during the next phase of total bed rest. The recovery phase demonstrated the usefulness of the exerciser in helping restore metabolic functions degraded by simulated weightlessness.
after these guys finished their bed rest studies, they used this exercise machine to monitor their parameters while they were getting back in condition.
Project Bedrest success led to the Total Body Exercisers test under actual weightlessness conditions, produced during aircraft parabolic flights. NASA subsequently adopted Project Bedrest's exercise protocols for future space missions that supported astronaut health and fitness.
The oxygen environment, the lack of pressure of oxygen, and the problems associated with then bed rest, which showed how the body sort of deteriorated if it wasn't exercised, led to development of exercise programs in space and showed what we should look for in time in conjunction with NASA.
Ultimately, Air Force space medicine research to mitigate the effects of weightlessness on human physiology contributed to improved protocols for the treatment of osteoporosis on Earth. Brooks' scientific ingenuity applied to weightlessness issues was also leveraged by NASA to advance spacesuit development. The Air Force had pioneered the development of spacesuits before the dawn of the space age, when as the Army Air Corps, it supported innovative research. This research was inspired by aviation pioneer Wiley Post, who was the first pilot to fly solo around the world. Post's interest in developing the spacesuit's predecessor, the pressure suit, was based upon his quest to break the world aircraft speed record by flying at higher altitudes. In 1932, he conceived the idea of adapting deep-sea diving technology for high-altitude flights. Working with B.F. Goodrich Company's Russell Colley, who decades later designed NASA's Project Mercury spacesuits, Post produced the world's first practical pressure suit. Supported by the Army Air Corps, Post conducted a series of pressure suit tests at Wright Field, Ohio in August 1934. He used the School of Aviation Medicine's former Mineola Lab low-pressure chamber to test the specially designed pressure suit. This suit was modeled after the Haldane Davis Stratosphere flying suit. A month later, Post made the world's first pressure suit test flight. During several subsequent stratospheric flights, wearing the deep-sea diving-like pressure suit, Post discovered the jet stream while advancing the science of pressurized flight. Post had paved the way for Army Air Corps, academia, and industry's concurrent development of pressure suits that decades later led to their adaptation as spacesuits. The first practical step toward developing spacesuits was made during World War II. Army Air Corps flight suits were not designed to physiologically protect aviators at high altitudes. T-1 partial pressure suits were originally designed in 1943 to protect pilots from in-flight stresses produced by rapid acceleration in experimental jet aircraft. The Air Force led research and development efforts during the 1950s to produce full pressure suits for the X-15 rocket plane program.
In those days, the average airplane never flew above about 45,000 feet, say in mid-50s. And here's the X-15 coming along. It'll go clear out to 300,000 feet and Mach 5 and that sort of thing. So we needed to develop stuff that would protect the man. Well, when we got into that, we realized that the same equipment might very well protect a pilot or a crew member in a space capsule.
NASA selected the X-15 pressure suits for the Project Gemini manned spaceflight program, replacing the Navy's Mark IV pressure suit that Mercury astronauts had worn. NASA's reliance on Air Force technology and space medicine research led the space agency to forge a partnership with Brooks scientists to test and evaluate commercially made pressure suits. Pressure suits, resembling science fiction-like spacesuits, had been produced by industry and America's armed forces during the first 2 decades of the space age. However, none of them fully met all the functional requirements needed to successfully perform in the harsh and unforgiving environment of space. Spacesuits needed to provide a stable internal pressure and mobility. supply breathable oxygen and eliminate waste carbon dioxide, regulate temperature, provide a means of collecting and containing solid and liquid waste, and provide a communications system. Brooks scientists had established a reputation for spacesuit-related research during astronaut candidate studies using the total body volume meter. The tank-like device used by submerged test subjects produced data on nitrogen narcosis-induced rapid decompression that Brooks scientists provided to NASA. This information was useful in helping the space agency develop spacesuits for extravehicular activities, commonly called spacewalks. School of Aerospace Medicine scientists at Brooks also designed spacesuits that prevented the loss of pressurization during extravehicular activities. During the 1980s, Brooks scientists helped NASA develop for space shuttle crews a new launch re-entry suit. NASA needed the new spacesuit based on past shuttle orbital missions that had exposed astronauts to prolonged periods of weightlessness. This scenario, which caused orthostatic intolerance resulting from body fluid loss, potentially exposed astronauts to G-force-induced loss of vision or consciousness. Brooks scientists, Drs. Bill Sears, Dick Bancroft, and Julian Cook, also developed a set of criteria for pre-breathing in space to prevent decompression sickness, what deep-sea divers call the bends. The Brooks scientific community contributed to other advances made in spacesuit development, including the advanced crew escape suit that space shuttle crews had used since 1994. Air Force contributions to spacesuit development greatly improved astronauts' capabilities to work and thrive in space. What remained underdeveloped 2 years before man first set foot on the moon, however, was NASA's understanding of vulnerabilities posed by a 100% oxygen spacecraft environment. NASA officials believed that the pure oxygen environment used for Apollo 1, America's first three-man space capsule, was the most environmentally suitable means for ensuring human survival beyond Earth's atmosphere.
We had 100% oxygen environment in our spacecraft from the beginning, from Mercury, Gemini, and now Apollo. We'd never had any trouble with that. We knew 100% oxygen is a dangerous thing, and if you had a spark in that environment, you're in real trouble.
Space medicine research had addressed the pure oxygen issue through space cabin simulations conducted at Randolph and Brooks Air Force bases in San Antonio during the 1950s and 1960s. This research, however, contradicted NASA's belief in the effectiveness of a 100% oxygen environment for spacecraft.
We told NASA, you shouldn't be using 100% oxygen. It's not a good environment. We've seen that and we've proved it, and they went ahead and did it anyway.
NASA and the Air Force, nevertheless, paid the ultimate price for using pure oxygen systems. America's space program suffered its first fatalities at Cape Canaveral, Florida, and Brooks Air Force Base in January 1967. During a routine pre-launch test of Apollo 1, an electrical spark ignited combustible material in the pure oxygen-saturated capsule atmosphere.
And a spark occurred, and fire went right away. You had this tremendously high-pressure oxygen environment, and we had a lot of Velcro in that spacecraft.
Astronauts Gus Grissom, Edward White, and Roger Chaffee died instantly in the flash fire that destroyed the spacecraft.
So the crew were killed with actually from the inhalation of carbon monoxide, and that was a real terrible disaster.
A month before the Apollo 1 tragedy, two Brooks airmen were unaware they would meet a similar fate. "20-year-old Airman Richard Harmon from Auburn, New York, and 21-year-old Airman William Bartley Jr. from Indianapolis, Indiana, were in San Antonio for Christmas. They spent the holiday at the home of a fellow physiological training specialist. Ironically, this technician and future San Antonio businessman witnessed their deaths while operating an altitude chamber at Brooks Air Force Base.
They weren't going home. So I said, come on over, spend Christmas with us. So the two of them, Harmon and Bartley, came over, and my wife had gotten to know them anyway. And now, spending the time at the house, she got to know them even more. They were just two really, really nice guys. And then 1 month later, we had the accident.
News of the Apollo 1 fire did not alter plans at Brooks to use a 100% oxygen environment in a 67-day low-pressure chamber test. The experiment was part of a long-term Air Force validation program to establish design criteria for the pressure and composition of atmospheres that might be used in future spacecraft design.
So the two of them, Harmon and Bartley, go in. I take them to altitude, and I hear, and at that time there was no communication other than a microphone where you had to push a button. In other words, there wasn't a live audio at all times. No, you had to pick up a mic. And we didn't have visual with this one either. There was a porthole on the airlock. So I heard the door open, and then all of a sudden I hear sounds of somebody running, because there were metal floor panels. I heard somebody running, which was really odd. You know how when you have your boots and you're running on the metal, and the metal panels are on the metal rails, so it's making a lot of noise. So I got up, looked up through and saw the porthole, and was flames. And I swear to this day that I saw something move by. That I'm not sure of, but there were flames, and I immediately dumped the valve and started screaming. And there's nothing you can do until the pressure equalizes.
The 100% oxygen environment created conditions conducive for a flash fire that consumed the chamber. A spark had ignited oxygen-saturated material.
One of them, when he was walking across the floor in the main chamber, there was a wire that was actually between the floor and the side of the chamber, and when he stepped across, it arced. So that person caught on fire and took it to the other person. Because again, what I remember was that other person was found in the airlock protecting himself from that person. So one brought it to the other, and which would be a natural thing. I mean, so there was nothing that they could do. And there was nothing we could do until the pressure equalized.
Brooks Airmen paid the ultimate price for America's space program only days after NASA had suffered its first fatalities. Like the Apollo 1 crew, Harmon and Bartley's lives ended as a consequence of what the fire had produced.
It was similar to the same sort of thing happened, because what happens is anything that's in there gets burned, and it's not and that's the source of what actually kills the individuals, is the products that are produced, the carbon monoxide that's inhaled.
Air Force investigators discovered what NASA had learned in the Apollo 1 fire. Oxygen-saturated materials supported combustion in a pure oxygen environment.
And these young men were there going through their stuff, and as a matter of fact, the conclusion of the examining board that looked into that showed that it was probably due to a break in Teflon wiring, which had been put in for a safety procedure to prevent difficulty. Didn't know at that time whether the high oxygen environment, what it caused. It most certainly supported combustion, so it created a fire, and there was presumably a break in the Teflon, which became brittle in a 100% oxygen environment.
The tragic loss of the astronauts and airmen, only days apart, resulted in improved safety measures that allowed America's manned spaceflight program to continue. NASA and the Air Force refocused their commitment to ensuring the survival of personnel who supported America's space program. Brooks scientists also relied on earlier Air Force research to support NASA's programs designed to safeguard lunar explorers. Technology developed from Air Force nuclear flash blindness tests provided the source for Brooks' scientific innovation that contributed to astronauts Neil Armstrong and Buzz Aldrin's successful mission to the Moon. The space program benefited from Air Force research that developed aircrew vision protection during post-World War II atomic testing. The Defense Department was mostly concerned about the physiological effects on aviators involved in aircraft delivery of nuclear weapons.
When they discovered that even though the effects of the nuclear weapon had went out to about 10 or 12 miles, which was far enough, but the effects on vision went out as far as you could see it.
Specifically, the Air Force wanted to protect airmen from the effects atomic weapons posed on vision. Atomic testing had produced in military volunteers thermal pulse-induced changes in visual acuity, retinal scarring, after images of the blast, and light blindness, the latter lasting for several minutes. Flash blindness was dangerous to aircrews because it impeded their ability to see flight instruments that allowed them to safely fly the aircraft. The Air Force produced a series of goggles and helmet visors for aircrew flash blindness protection. The most effective of these was a gold-layered helmet visor. A similar gold layer was applied to astronaut helmets to protect them from damaging ultraviolet rays on the Moon. School of Aerospace Medicine ophthalmology researchers at Brooks are credited with adapting nuclear flash blindness technology for the space program.
That visor was used, and nobody had to pay extra for it. It was used in the exploration of the Moon. Dr. Don Pitts, who was a lieutenant colonel then, was the prime project manager on the project on ultraviolet energy in space and what effect it would have on the Moon exploration. The effect it would have is that it would cause like a welder's flash had they not had the protection and would have to take a day or so to recover, which was not compatible with the project of getting back from there. There were certain windows that had to be met, and if you didn't meet those, you're in big trouble.
While Air Force technology helped lunar explorers avoid trouble posed by ultraviolet, light-induced sunburn to their eyes, it also played a role in protecting astronauts from space radiation. School of Aerospace Medicine's Colonel John Pickering, together with doctors Ralph Allen and Oscar Ritter, had pioneered pre-NASA-era space radiation research. Their subsequent work to support America's early manned spaceflight program involved developing ways to shield spaceships from cosmic radiation. Shielding spacecraft from space radiation, however, was only part of a larger problem.
In the early days of spaceflight, there was a lot of concern about the potential hazards of solar flare protons. The astronauts were being exposed to solar flare protons, and that was an ionizing radiation problem.
Ionizing radiation, such as X-rays and gamma rays, are undetectable by human senses. Air Force scientists discovered that space radiation's damage to the human body is cumulative, based on total doses received and duration of exposure. NASA's need for Air Force research that focused on mitigating space radiation's bioeffects led to the creation of the School of Aerospace Medicine's Radiation Sciences Lab.
Our physics group was actively involved with NASA to help them in developing dosimeter systems to measure the radiation levels on the astronauts in the space missions.
The Air Force Lab developed for NASA passive space crew dosimeters that measured ionizing radiation levels in astronauts. From 1964 to 1970, Brooks Air Force Base developed dosimeters were worn by all astronauts during every space mission. Brooks scientists also went a step further to help NASA understand the long-term health hazards of space radiation.
Another device which was very important at the time was we built a solar flare simulator, which is a very massive, well not massive, but device that we could put in front of cyclotron beams and linear accelerators to degrade the proton levels to energies that were needed to study the biological effects of space radiation.
Protecting astronauts' health from space travel hazards was only a small part of the Air Force mission at Brooks that supported NASA programs. The space agency had relied on Air Force space medicine expertise for decades, based on Brooks scientists' development of aerospace medicine that contributed to enhanced aviator performance.
Our strongest memories are when Dick Scobie came here for evaluation prior to being a test pilot and prior to being selected as an astronaut. So everyone knew where Brooks Air Force Base was. If you lived here in San Antonio, it was where the pilots came.
Brooks was also the place where astronauts received G-force acceleration training. Since the 1990s, astronauts have been exposed to G-force space shuttle launch profiles in the base's centrifuge. In 1998, 77-year-old astronaut John Glenn participated in centrifuge training at Brooks in preparation for his historic return to space. In 2010, Brooks served as the venue for another historic return to space with Project Red Bull Stratus. The initiative, sponsored by the energy drink company Red Bull, involved eclipsing the world freefall balloon jump record held by Air Force pioneer parachutist Joe Kittinger. The planned 120,000-foot freefall parachute jump required extensive high-altitude equipment testing. The project planners found at Brooks the perfect research facilities they needed to help them prepare for the stratospheric flight.
This is truly a flight test program in all natures. We're not just jumping in a capsule and going to altitude and jumping out. We've done a full training session, which is a progressive buildup. That was one of my requirements to really see this happen, was to be able to put the team together that was needed and to be able to progressively build up not only the jump process to train the jumper, but also for developing the capsule systems, life support. We have redundant life support. And so this buildup over time, over the last 3 years now, has kind of come to this point where we actually get to test what we've been building for 3 years. So it's exciting for me and the entire team to be able to be here at Brooks, which has some incredible history. It's the start of the space program. To be able to come here